All right, hello class. Good afternoon. Um, I got started a little bit early because I was ready, so I just figured I'd just go for it. Um, let's see. Boy, I would, if you're taking an AP test this year, I would, whether it's AP Physics 1 or some other math one, definitely make sure you take a look at the sample exams for 2020 because the exam's very different. I just in the previous class I was just going over an AP Physics C exam, and the questions were just completely different from what they usually are. Sophia says I should buy an IKEA shark. Why do you say that? And is IKEA even open right now? Has anyone ventured to IKEA? I don't know. Hey Jackson. Oh yeah, it's my hardcore crew. Okay, so let's get right into it. Um, so I've got the May 2018 Time Zone 1 Paper 3, and I'm going to be doing questions 2 and 7 for you guys today. One thing I want to point out is next week you are going to have a final exam, quote, final exam. You can work in groups of 2. So it's a little bit different rules, and we're not going to have any class for the first 3 days of next week, and then so that'll be for you guys to work on the exam because it's a little bit longer, and then you'll submit it, and Thursday and Friday we'll start astrophysics. Okay. So, as I said, I'm doing questions 2 and 7, so let's dive right into it. Okay. An experiment to find the internal resistance of a cell of known EMF is to be set. The following equipment is available: a cell, an ammeter, a 10K resistor. Draw a suitable circuit diagram that would enable the internal resistance to be determined. Well, I don't even think you really need the 10K resistor because literally, well, we'll just do this. We'll say just a straight up series circuit. Right, like that. That's the 10 ohm resistor. It is noticed that the resistor gets warmer. Explain how this would affect the calculated value of the internal resistance. Okay, so if I look at this circuit, the total resistance of the circuit would be the internal resistance plus the 10 ohm resistor. Okay? And then that means that the current that flows would be V over R tote. Now the voltage is the EMF of the battery, which it says is known. Notice how it says it's a known EMF. And then the total resistance is R plus 10. So basically the ammeter tells us the current. We know the EMF, and so we could solve this equation for the internal resistance. But here's the thing. Resistance depends on temperature. Why is that? If you heat a resistor up, then you're causing the atoms to jiggle more. And that jiggling, it turns out, is going to take electrons that were originally trapped to the nuclei and free them in order to conduct current. So you have more electrons available to conduct current when you raise the temperature. And so what happens is the resistance will go down as the temperature increases. So basically, if this resistor gets warmer, then it's not going to be a 10 ohm resistor anymore. It might be more like 9 ohms or something like that. So the equation that we solve would be different. So that's what I would say, something to that effect. Outline how using a variable resistance could improve the accuracy of the value found for the internal resistance. So basically what we're doing here, because we only have a single 10 ohm resistor, we're using a single point. So we're basically putting all our eggs in one basket. We're using a single point. A more powerful way to determine the internal resistance would be to take many points and try to get a trend line. Okay, so if this wasn't a 10 ohm resistor, if it was a variable resistor, we could just call that big R. Okay, so that would be the amount of current that flows. So let's go ahead and just like play around with this equation a little bit. So what if I wrote it as little r plus big R equals E over I? Okay. And then what if I subtracted so I'm going to write it like this. Big R equals E times 1 over I minus little r. Okay? So what if I made a graph where I have big R, which is the value of the external resistance, versus 1 over I. So if we compare that to our standard, equation of a line, we would have y equals, and then because r is like y, 1 over I is like x, so the slope is going to be the EMF, and then the intercept is going to be minus r. So basically this would be a straight line. We would take our data and we would get a straight line, and we could use the line of best fit and extrapolate it back. The intercept would tell us this intercept would be minus r. So that's a more powerful way. It's using many data points to get the value instead of 1. All right. So that was it for question 2. Let's take a look at question 7. I think I said 2 and 7. 2 and 7. Okay, looks like we got another PV diagram. PV diagram shows the cycle ABCA of a heat engine. Jackson asks, is the final in groups? It's groups of 2, so you can work in pairs. So maybe take your normal quiz group and split it in half. Or you can work individually, it's up to you. The working substance of the engine is a 0.221 mole of ideal monatomic gas. At A, the temperature of the gas is 295 Kelvin and the pressure is low. The process from A to B is adiabatic. Show that the pressure at B is about 5 times 10 to the 5th Pascal. So again, we have this adiabatic. For adiabatic, we have P initial, V initial to the 5/3 equals P final, V final to the 5/3. This is the equation for adiabatic gases. Okay. Of course, for isothermal, you have P initial, V initial equals P final, V final. All right, so depending on what kind of process it is, you have a different relationship between the pressures and volumes of the initial state and the final state. But this is adiabatic. So you'll notice that the volume is measured in 10 to the minus 3. Whoa, could I rotate this? Holy crap, I didn't know I could do that. Rotate that. So we can see that the volume is measured in 10 to the minus 3 cubic meters. Because I have volume on both sides of the equation, those units are going to cancel out, so I don't need to worry about the 10 to the minus 3. Okay, so the initial state we're calling A, and the final state we're calling B. So we know that the volume at B is 2. And we know that the pressure at A is 1.1 times 10 to the 5th. And we know that the volume of A is 5. So I can use this to solve for P sub B. And we get about 5.1 times 10 to the 5th. Pascal. Cool. For the process BC, calculate in joules the work done by the gas. So work is the area under the PV diagram. So what I would do is I would, and we want to know for B to C. So B to C is this segment. So I want the area under that. So that's like all of this area. Okay, that amount of area. So I calculate that. So I know that the height of that rectangle is 5 times 10 to the 5th Pascal. Okay, so they told us that already. So it's going to be width times height. That's unfortunate unit or unfortunate variables there, but this is work. This is width. The width is 3 because it's 2 to 5. 3 times 10 to the minus 3. And the height is, as it said, 5 times 10 to the 5th. So it looks like we're going to get 15 times 10 to the 2, which is 1,500 joules is the work done. Oh, that was I. So this would be II. Calculate the change in internal energy of the gas. So the formula for internal energy of the gas is 3/2 nert. Okay, which could also be written as 3/2 PV. So if we want to know what is the change in internal energy, it would be U final, which is the final state is C, minus U initial, which is B. So that would be 3/2 pressure at C, volume at C, minus 3/2 pressure at B times the volume at B. All right. Now, one of the things we would notice here is that the pressure at C and the pressure at B are the same. These are both going to be the 5 times 10 to the 5th pascals. So really this is going to be 3/2 times that pressure times the change in volume. Pressure times the change in volume, that's just the work. So it's going to be 3/2 times the work done, which would be 2250 joules. Okay. The third part, we want the change in the thermal energy transferred to the gas. So thermal energy, that's another word for heat. And so what I'm going to use is the first law of thermodynamics, which says that delta U equals Q minus W. So this is the change in internal energy of the gas. This is the work done by the gas. So we calculated that the work done by the gas was 1500. And we calculated that the change in internal energy was 2250. So adding those together, we get 3750 joules is the heat added to the gas. Part C. Part I. The process B to C is replaced by an isothermal process in which the initial state is the same and the final volume is 5 times 10 to the minus 3. Okay. Explain without any calculation why the pressure after this change would be lower if the process was isothermal. Okay, so basically we're going from here to here. This is what we would call an adiabatic, an isobaric process, because the barometer reading, pressure reading, is going to be the same. However, if we had a isothermal process, we're keeping the temperature the same. The gas is expanding, and it's going to have this kind of relationship. So we can see from this equation that P final, for an isothermal process, you have PV equals a constant. So that means that P equals a constant over V. So we can see that as the volume increases, the pressure decreases. So, yeah. So yeah, I would say something like PV equals constant for isothermal. So as the as the volume goes up, the pressure has to go down. So it has to drop below the pressure in B. All right. Let's see. 2. Determine without any calculation whether the net work done by the engine during one full cycle would increase or decrease. Well, um, so if we look at it, uh, so what we had before, so the work done on, so let me move this out of the way. The work done is the area enclosed. The work done in a cycle is the area enclosed. So if our cycle is this cycle that's shown, then the work done is all of this. Okay. All right. But what if we do, instead of B to C being isobaric, what if it is isothermal? Now our process is basically the area enclosed would be this, only that portion. Okay, so we can see that the area enclosed is now less by comparing those two squiggles. We can see that the top squiggle is more area. Okay, so I would say something to the effect that the area enclosed went down, so the work went down. All right. Part D says, outline why an efficiency calculation is important for an engineer designing a heat engine. Well, efficiency is the useful work done divided by the heat that goes in. So basically, we want to make sure that we do enough work, or we want to make sure that we use as little fuel as possible. Okay, so that's why it's important to know. The higher the efficiency, the less fuel we need, and that's important for cost purposes. Okay, so something to that effect. All right, the three of you that watched, please, if you wouldn't mind, spread the word on the quote final exam. It's not going to be worth as much as a traditional final exam would be, but I wanted to give you guys some kind of a summative test on everything that we've learned this semester so far. So that's what that will be. In fact, it's available right now, so you can get started if you want to. I hope you guys have a great afternoon, and I will talk to you tomorrow. Bye.